In the following example, we want to show that P then Q or R is equivalent to P and not Q then R, and it's equivalent to P and not R then Q. Well, in order to do that, you can basically construct the truth table. You can also use the fact that A then B is equivalent to not A or B. So let's see what happens here. My A is here, my B is here. So I can write this as not A, not P, or Q or R. So here I have not P or Q or R, right? Let's take a look at this. This is my A and this is my B. Not A is going to be not P and not Q, or B, which is R. But by De Morgan's law, we can just distribute this into parentheses. We get not P or not Q, which is Q or R. So far, these two are equivalent to each other. Let's take a look at this one. I have A and B. So what I have not A, which is not P and not R, or Q. But again, by De Morgan's laws, we're going to distribute this into parentheses. We get not P or not R, which is R, or Q. So as you can see, these three are equivalent to each other. So what's the use of this? For example, you have the following statement. If n is prime, then n is odd, or n is 2. This is P, then Q or R. If we try to rewrite this using like P and not Q, then R, it says that, hey, if n is prime and n is not odd, then n is 2. Let's take a look at another statement equivalent to that. You have P and not R, then Q. What's the meaning of that? My P is n is prime, so it says if n is prime and not R, and n is not 2, n is not 2, then Q, then n is odd. So using equivalent statements help us to rewrite some complicated statements in simpler version or simpler format. Let's take a look at next example. I'm going to write the negation of each of the following statements here. The very first statement says if P is a square, then P is a rectangle. We have some more examples and statements, so try to write it the way that it doesn't overlap with the rest of the statements here. I think this is enough. So let's write down the negation of the first statement. If P is a square, then P is a rectangle. So remember that P, then Q is equivalent to not P or Q. So if you try to write the negation of P, then Q, this is equivalent to P and not Q. So the equivalent, you're just going to copy down P. If P is a square, I'm going to write down P is a square and P is not a rectangle. Let's take a look at another statement. If today is New Year's Eve, then tomorrow is January. So number B, the hypothesis, today is New Year's Eve, We're going to copy this down. Again, we're following P and not Q as the negation of the implication. Today is New Year's Eve. And tomorrow is not January. If the decimal expansion of R is terminating, then R is rational. So its negation is going to be, we're going to copy down your hypothesis, the decimal expansion of R is terminating and R is not rational. If n is prime, then n is odd or n is 2. So take a look. Here you have P, then Q or R. So this is P, then Q or R, which equivalently can be written as not P or Q or R. If we try to find a negation here, the negation of P, then Q or R is the same as the negation of this statement, not P or Q or R, which is going to be not P, which is P, and not Q, and not R. So take a look at D. N is prime. We just write down the very first statement, and not Q, N is not odd, and N is not 2. Question says, use truth tables to establish the truth of each of the following statements. A conditional statement is not logically equivalent to its converse. So basically, in order to use the truth table here, remember the conditional statement. For this case, what do we have? We know that we are working with the conditional statement. It says it is not equivalent to its converse. So for part A, what do we have here? The conditional statement P then Q is written as P then Q. Its converse is Q then P. So let's take a look at the truth table. PQ, P then Q, Q then P. True, true. False, false. True, false, true, false. We're using the basic definitions that we did before. True then true is true. True then false is false. False then true is true. False then false is true. Now Q then P. Be careful about the order. Q then P. True then true is true. False then true is true. True then false is false. And finally, false then false is true. So as you can see, these two are not equivalent to each other. So P then Q is not equivalent to Q then P. A conditional statement is not logically equivalent to its inverse, right? Remember the definition of inverse. For the inverse, we have not P, then not Q. Inverse, not P, then not Q. So what do we need? We need not P, we need not Q as well, and then not P, then not Q. So here for not P, you have false, false, true, true. And for not Q, you have false, true, false, true. So not P, then not Q. Not P, then not Q. False, then false is true. Let me move this here for the inverse. So false, then false is true. False, then true is true. True, then false is false. True, then true is true. So as you can see, if you compare P, then Q, and its inverse, they have different truth values. So far we showed that P then Q is not equivalent to its converse. It's not equivalent to its inverse, but it is equivalent to its contrapositive. So let us take a look at not Q, then not P. Let me move this a little bit here. So we can build not Q, then not P. Not Q, then not P. So take a look from not Q to not P. We're changing the order, right? Now here from not Q to not P. True, false, then false is true. True, then false is false. False, then false is true. True, then true is true. So now comparing P then Q with its contrapositive, you can easily see that they are equivalent to each other. So we work with converse, we work with inverse, and we can easily see that P then Q is equivalent to not Q then not P. Let's take a look at another example here for you. We want to show that P then Q or R is logically equivalent to P and not Q then R. So you can use truth table, but I encourage you to use the laws to show that these two are equivalent to each other. So remember that A then B is equivalent to not A or B, right? So here you have P then Q or R on your left-hand side, which can be written as not P or Q or R. Not P or Q or R. And then on your right-hand side, you have P and Q, then R, which is not P and not Q or R. By De Morgan's law, it is not P or not Q, which is Q or R. So as you can see, these are all equivalent. Let's take a look at P and Q or R and show that it is equivalent to P and Q or P and R. For this one, we cannot use the laws because it's already one of the laws. So what are we going to do? We're going to basically use the truth table for it. So here I have P, Q, and R. I have P and Q, I have P and R, and then I have Q or R. And finally, we have P and Q or R. Now let me move this a little bit here. I think we need more space. Then we have P and Q or P and R. So let's begin. True, 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 true. Then false, 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 false. True, 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 false, false. Standard combination of these statements. Then you have true, false, true, false, true, false, true, false. Very well. So P and Q. Connecting these two using and. True and true is true. True and true, true. True and false, false. True and false, false. False and true, false. False and true, false. And then false and false, which is false. False and false, which is false. Okay. P and R. Now we're combining these two using and. True and true is true. True and false is false. True and true is true. True and false is false. False and true, false. False and false, false. False and true, false. False and false, false. Then Q or R. Okay, let us connect Q and R using or. True or true is true. True or false is true. False or true is true. False or false is false. True or true is true. True or false is true. False or true is true. False or false is false. Very well. In the next step, we're going to combine P and Q or R. P and Q or R. So you have true and true, which is true. True and true, which is true. True and true, which is true. True and false, which is false. False and true, which is false. False and true, false. False and true, false. False and false is false. And finally, in the last step, we're going to basically combine P and Q or P and R. P and Q, P and R, using or operator. True or true is true. True or false is true. False or true, true. False or false is false. Then we have false or false, which is false. False or false, the rest of them, as you can see, are false. So what does it tell us? It tells us, hey, these two are equivalent to each other. So for the first one, we used the laws. For the second one, we used the truth tables. Why is that? Because this one is already a law itself. To prove the law, we need to use the truth table. You're basically distributing and over or. And this is the distribution law, as you remember. Okay, let us move on to next example. Here, P then Q then R is equivalent to P and Q then R. So for this one, I'm not going to use the tables. I'm going to use the relationship that we defined before. A then B is equivalent to not A or B. So here we go. I have A, which is P. This is my P. Let's just label this so you can identify this a little bit easier. A, B. So on the left-hand side, you get not P or Q then R. But inside the parentheses, you still have implication. So you can write it as not P or not Q or R. So basically what you have not P or not Q or R, right? Let's take a look at the right-hand side. This is my A and this is my B. So on the right-hand side, I have not A, not P and Q or R. So by De Morgan's law, you just need to distribute negation into the parentheses. You get not P or not Q or R, but this is nothing but not P or not Q or R. So as you can see, these two are equivalent to each other. So this is the way that we basically work with different types of statements showing they are equivalent or not.